Next time we talk about the different mode, TM mode and quasi-TM mode. Next time.
Next time? Last time?
Yeah, next time.
Okay. I will just go through what I said last week because we almost finished because I almost finished, so let me just quickly go through what we have told last week, okay? Okay, so to remind you what you learned last week. For the second part of the chapter 1, for this one, last week we discussed about materials. Actually, it's about materials. There are some materials. Why do we need to talk about materials? Because I want to tell you about two important parameters, epsilon r and loss tangent, right? These two, what are them? What are them? Okay. For the student, if you only want to design circuits, maybe you just key in these parameters in your ADS. That's it, maybe. But you know, first of all, they are not a constant for all the frequencies. They depend on frequency. So we will have some method to measure epsilon r and loss tangent. But before we measure it, maybe we should talk about how to describe them. Why do we have them? So materials, we have to simplify the groups of materials. You can simplify that as to only insulator, semiconductor, and conductors. Or maybe you can see that those are only simulator and conductors. The difference between insulator and the conductors is their conductivity. The value of conductivity is different. If the conductivity is very large, it's a conductor. And if it is very small, it is an insulator. That's it. It's very easy to understand. So if the conductivity is very large, it is a conductor, and the conductivity, the parameter to describe is that a conductor or not, the conductivity equals to 1 over the rho, which is a resistivity. They are like the opposite way to describe the same thing, the conductivity and the resistivity. Okay, fine. Then from here. Okay, so and numbers, and I also tell you one of the important equations. But I'm trying to just quickly review all very important things. So if you forgot what I told last week, maybe you can quickly follow. Okay, this one is very important. The skin depth means how deep your microwave can penetrate inside the metal. How deep equals to 1 over the alpha. The alpha is, we discussed the alpha in the last week. Alpha, it is the propagation constant equals, the gamma equals to alpha plus j beta. We will have more explanation about alpha and beta later in the beginning of today's class later. Okay, so this is the same alpha. If you propagate a wave, there is an alpha, and the alpha means attenuation. Chinese is 衰减. Alpha describes the attenuation. If the alpha is large, attenuation is also large. Okay? Okay, alpha means attenuation. So you can see that the skin depth equals to 1 over alpha. So if the alpha is very large, which means your conductivity is very high, then your wave cannot penetrate inside the metal. Okay? I think you can understand the physical meaning of this part. And for the last part, is more, you have more component to describe this phenomena equals to the square root of 2 over omega mu. This is a conductivity, right? Conductivity. Yes, you can see that if you have large alpha, means you have large conductivity. And the mu always equals to, in our case, u always equals to mu 0. So this is a constant. And there is omega here, is 2 pi f. So your frequency, if your frequency is higher, then your skin depth is smaller. Okay, you can see the equation. This is a very useful equation. You might see them later. You might see them later in the near future. Okay, so this is a skin effect. And in the contrary of the conductor, you have the dielectrics. Dielectrics means something is not a conductor, or the conductivity is very small. So therefore, because if that is a conductor, your microwave cannot pass through the conductor. But if that is not, it's a dielectric, your microwave may go inside the dielectrics. Okay? So we will have a lot of story about dielectric. For example, FR4, or Teflon, or maybe gas, water. Okay? You have materials, you have the microwave can go inside that. Those are dielectric. And usually their alpha is small, but not 0. Those are small. And the conductivity is small. Okay? So we need to discuss something. Actually, for the second part, the main goal. Well, our goal. GAOL, right? GOAL. Okay, goal. 我拼错，目标 goal, right? Goal. Right? Correct, right? Our goal is to find out what is the more general equation about the wave equation. More general. You will have alpha is not 0 but small, or you will have a conductivity is not 0 but small. If they are 0, you don't need to deal with that. We already told you. I already told you that what is lossless. If this one is 0, that's lossless. But I'm talking about we try to have a more accurate equation to describe the wave. Okay, this is why we spend so much time to read another textbook to go through what are the difference between conductor and insulator, or you say dielectrics. Okay. Those are different. So for dielectric, actually, we will deal with that in here. In here, B equals to mu H and D equals to epsilon E, and the mu equals to mu R multiplied by mu 0, and the epsilon equals to epsilon R multiply epsilon 0. For that case, for these two answers, maybe it is still a lossless material. it depends on your epsilon r is that is a complex or not, or only a real part. If your epsilon r is a real number only, that's a lossless case. It's still the same as what we deal with the lossless case. But if epsilon r, if that is a lossy, if that is a lossy material, your epsilon r is a complex number, and you will have more problem to deal with. Okay, and we try to explain what is this epsilon r, right? We talk about the epsilon, this epsilon. It's possible because of we have the polarization. You have something. You have when you have an E field, your atoms will be polarized, and your epsilon 0 times E is not the only part, and you will also have the PE, another vector, more than something, okay? And this something can be combined together, and you will get a result, and which is your epsilon. Actually, it is epsilon 0 multiplied 1 plus something else, okay? And the result is, so this is your epsilon, this is your epsilon, and because it is when it is not just only a pure conductor, your conductivity is not 0, so you have one more term here, you have one more extra term. So your second equation of your Maxwell equation will become this form, which is a complex number color. This is a complex number multiplied by your E. Okay, this is a complex number. So the definition of loss tangent will equals to the real part of this number divided by the imaginary part of this number. This is a definition of the loss tangent we usually use to design our circuit. Okay? This is one of the important results. So you can see that if your conductivity is 0, actually there is maybe some terms related to loss. Even your conductivity is 0 here, and it's a ratio between these two, even as the 0. And you will see the explanation that epsilon double prime comes from the damping of the atom, right? You remember that? If there is an E field on your material, there is a vibration damping of vibration. Okay, so you will see that your loss tangent is a result. It's a combination. It's a combination of result from conductivity and the damping. Not only just conductivity. Yeah, I want to fix what I said a couple of minutes ago. According to this equation, yeah, if you want to see that very accurate, your loss tangent comes from part of your damping of the dipole and the part of conductivity, and it's accumulation of this result. If there is no damping and there is no conductivity and loss tangent is 0, then you don't have loss. Okay, it's our definition. It's theoretically. Okay, one of the review, and we will just explain. we just explained epsilon r and the loss tangent, those two things, and you have some sense about where did they come from. After you will have the sense of lossy material, you know, okay, lossy, what's lossy? Oh, means your loss tangent is not zero, and then maybe you will have a conductivity. Then, so you come back to see your, you go back to the place we derived the Maxwell equations. You will see that, oh, for Maxwell equations, maybe we will have the J, because when your conductivity is not zero anymore, you will have one more extra term, and I think one of you already tried to help to derive the new equation, wave equations. Yeah, you do the second curl. This is the first curl, and do the second curl, and you find out. Finally, you got very similar form of the. This is wave equations. Actually, a lossy case. LOSSY. It's a lossy case of the wave equation. You got this one, and also there is another one for H. Right, for magnetic field, and very similar because the equations are similar, so you might have very similar thing. Or maybe not, because we just stop here. They are different because for this one you have this term, but for magnetic field you don't have that term. So maybe we just stop to discuss about that. We just talk about only E field only. Okay, so this is Laplace of your E field plus omega square mu epsilon. Now you need to multiply an extra term and multiply E field equals to 0. This is the extra. This is some more term because your conductivity, it is not 0 anymore. It is some small number, but they exist. It exists, right? So you have this term. If this is 0, you don't have this term, and then multiply by 1, and then equals this one is k squared, right? So this is new. This is new, and because of this is there's a real number, real part, and this is an imaginary part. So you know you will deal with something which is a complex number. Before we try to solve it, at the beginning, we define a new parameter. We call that a complex propagation constant, which is complex gamma. Gamma equals to alpha plus j beta. Okay, you have the real part, you have the imaginary part, and we try to make the case, the lossless case and the lossy case, we try to make them have the same result. Okay, so we define that if your gamma square equals to minus k square, because of this term, there is a jk. If alpha is 0, it should equals to, this one should equals to jk, right? So you need to use this term to instate your old equation. Then you will find this. Did you see that? This is old number, right? This is old equation. For this, try to understand why we define that. This is what we did before. K equals to omega times the square root of mu epsilon, right? Remember that? This is a definition, right? But now it is complex. So we try to not solve that yet, but we know there will be a real number and an imaginary number. number. We know that. So when we start, we try to have something. This is a new guy. It is a complex. You have a real part and imaginary part. We try to fit our result to our lossless case. This lossy case and the lossless case. We try to make them identical. Just try to make them the same if alpha equals to 0. For alpha equals to gamma equals to alpha plus j beta. If alpha is 0, they are the same. So we find, if alpha is 0, they are the same, which means gamma squared will equals to minus k squared, and you obtain this new equation. Okay? Okay? And where does the minus come from? Okay, minus come from you have a j squared. J squared means minus 1. Okay? J is the square root of minus 1. So j squared is minus 1. Okay? So there is a minus here. So this is our new equation of a lossy wave equation. Okay, lossy wave equation. This is a lossless wave equation and lossy wave equation. To solve this equation, we use the same method. You obtain something here. See, this is a lossless equation. You have your EX is a function of Z equals to E plus multiply exponential power to the power J minus JKZ plus E minus times exponential to positive JKZ. This is what you should be very familiar with that because this is your quiz, right? Your quiz only have this part. When you see that here, it is minus JK, means this is the alpha is 0. So you have this term. Okay. But if alpha is there's some number of alpha, you should write down something here, and then you put alpha equals to gamma equals to alpha plus j, maybe k or beta j. Where is j and the beta? They are the same at this point, at the beginning. Beta equals to k. Okay. When will you see different? They are different. Well, they will be different in chapter 3. In chapter 2, maybe they are still the same. Beta and k, they are the same thing. Okay. For different types of transmission line, beta is different. But at this point, it's very easy to, okay, maybe you can write down alpha plus j, k, and then put this term here and also here. Okay, and this is our new electric field in the lossy material. Okay. Okay. And maybe if you have some example test, but because of time, maybe sometimes you need to do your job to read a book. Maybe you try to discuss with me that what I think maybe it's correct or not. Okay. So you see that here, right? So you just put everything here. You compare to these two equations. You realize that minus gamma square will equal to omega square times mu epsilon times this term and E, okay? And not E is the same. So minus gamma square will equal to this term. Let me circle it. This term equals to this term. Okay? Then your gamma will equals to this term. It's not very difficult, so you can do the job. And you just, the only thing you need to do is to deal with this and separate the real part and the imaginary part. You separate it, and then you know your alpha and the beta. Okay. Okay. And this page is telling you that for this time, K and the beta, they are the same. If you talk about lossy case, there is alpha and the beta, and the lossless case is K, okay? Or maybe lossless case, it is a case. Lossy case is a spatial. Let me say again. Lossless case, it is a spatial case of lossy case. If in your lossy case, alpha equals to 0 and beta equals to K. Okay? Do I need to say that again? We are too fast. Lossless case. Lossless case is a spatial case of lossy case. Lossy case, you have alpha, gamma equals to alpha plus j beta, and you have only j k, right? They are the same. Only if this term means this is that lossy case only if alpha equals to 0. Okay, so this page is telling you only this thing. So it's the same if alpha equals to 0, it is a spatial case. And one more important thing to tell you here is, now you guys, you have the concept of the phasor form, right? Phasor form. What is the phasor form of this one? Let me write this term. Let me write this term down, okay? Yeah, give me some more time to explain this one. It's a new thing here. If E is equals to something multiply exponential minus gamma z. Okay, I talk about a positive way only. If this one, you have this E field. Okay, very similar to your question, but this is a lossy case. For the lossy case, because gamma equals to alpha plus j beta. So your E field your E field, or maybe I just write Z and I don't need the vector, will equals to some magnitude multiply exponential minus alpha plus j beta multiply times Z. Okay? If this is okay. This one can be write down as, you can take the real part outside, will equals to E plus multiplied by exponential minus alpha z multiplied exponential minus j beta z. Understand? You can take this term outside. Alright, everyone? You learned this before, right? It's how to say that? It's a power. 指数对数英文怎么讲
Exponential.
It's not exponential. It's okay. That's a basic. It's a 忘记指数怎么讲？指数还是对数
Exponential 对数是 log.
Log and exponential. Is that okay? If there's a plus, means you multiply outside. Okay. This one, actually, you can see only a real part. It is a cosine beta z minus sine. You can omit that. Okay, so this is a cosine. Okay, this is for this term. It is a cosine function. So if your alpha equals to 0, means there is a cosine. This is a z, and you have the cosine function. And all your magnitude, it is e plus for only these two terms. Okay. But what is the equation of this one? This term is exponential to the minus alpha z. This is the function, looks like that. It's getting smaller and smaller. Because of this, there is a minus, right? This one equals to 1 over exponential to the power alpha z. For this term, you're getting larger and larger strongly according to your component, your distance, your z, right? And then you have the minus here is 1 over exponential to the alpha z. So it's like this term. Your attenuation, your red one here, it is this function. And for the rest of this term, you have this time domain, right? Exponential to the j omega t. If you put a t here or not, it's okay. It depends on is that a function of t or not. Okay, you can have this one, or like me, you can take this term out. You can have a beta z only. It's a cosine function. You multiply your cosine function to your red box. You will find this one. The blue one is your cosine function. Okay, and your pink one is your attenuation function. So if you multiply this function together, you get the red function. This red, you have this curve, red curve. This is a real situation, real shape of your wave when your microwave is traveling in a lossy media. Okay, I will stop here and we'll take a rest. Okay, okay, so makes sense, right? Blue one, there is no attenuation, and if you have alpha, alpha means you are getting smaller and smaller according to your z. And you multiply them together, you will become the red one. 你们都听得懂吗？这个没有到很难，它就是两个项，一个是 cosine 嘛，不会随着距离变的，它永远会这样子的。然后这个衰减项是粉红色的，它 exponential minus alpha z， 它会随着 z 越来越小，越来越小。为什么？因为它是负的次方嘛，所以它本来是
z 越大，那个数字越大，所以这个粉红色越小。把这两个函数乘在一起就变成红色。实际上，你的 point 就是在有损耗的情况下就会变红色这个。好，所以你在 lossless case 你在做的是蓝色的，那 lossy case 现在你要做红色这条，这样子。你们答案写的 loss， 你再看到 lossless， 你就是在做蓝色 ，lossy is red。Lossless is blue. Okay, let's take a little break and maybe we can discuss your quiz. If you think it's not fair and maybe I made a mistake, or you want to figure something out, maybe you can discuss with me. Okay, take a break.
你们觉得柜子，你觉得为什么没有分啊？还是说
Okay. So this picture is important to explain what is alpha. The alpha is attenuation constant can determine your attenuation, or you say the decrease, how your wave decrease, and you can also refer to this picture. Okay. So the red one is a real lossy. Your lossy microwave E-field. Actually, it's just we talk about E-field so far, right? E-field. Okay. So we apply very similar thing to loss case. For the lossless case, remember how we derive eta, right? The impedance about the wave impedance between E and H. This is where we derive it. And for you apply the same thing to here, and you will obtain your lossy, the ratio between E and H, which is the wave impedance. It is this one, and you can obtain this one. Okay, I just neglect the calculation and got the result. Okay, so if that is a lossy E field and a lossy H field, you will have this result. Your H field becomes this one. Then we can have a new quiz, right? Very similar quiz. But maybe I will leave this question to you, and you should try to apply lossy E and H field very similar to your quiz from lossless to lossy case. Okay? See you in the midterm, right? See you in the midterm for the lossy case if that is there's a material, you have alpha, then you maybe I will tell you what is the E field and tell me about the H field, and you give me the lossy wave, lossy E field and lossy H field. Okay? Are we good? Okay, not very difficult. Not very difficult. You have the equations here already. Why I tell you that it's not difficult? Because we have a more difficult part then. I'll tell you something more difficult then. Okay. Okay. Oh, before that, there's another case, another special case. If your wave is inside a good conductor, write down. If that is a conductor, and if that is if that is lossy material
and that is the lossless material. For the lossless material, your alpha equals to 0, okay? And for the lossy material, your alpha is close to 0, but not 0, okay? But if it is a good conductor, alpha is not 0, but still not small, and it's large enough, okay? Or you said maybe your conductivity is 0 or close to 0 or not 0. Can you tell the difference? I give you a number. It's 0 or maybe 0.001 or maybe 0.2 or some case like that. Okay. Or maybe a larger number, give you 0.5. Okay, those are case. Okay. 1, 2, 3. There are some different cases, and now it's a good conductor. You have a number, it's not very small. You have some number. Okay, so what happened here? What happened here? Okay, is that a good conductor? What is good conductor? Good conductor, the definition of good conductor means your J is larger than J omega D. This term is larger than this one. Or your this term is larger than this term. Okay, just don't see J. This term. Okay. I know this is the real part and this is the imaginary part. We just compare about the value, okay? Or in your math, when you calculate that, you can find this result or this result, okay? Okay? So it's something like what I just wrote down. And you have this one. So what happened here? I said when this term is larger than this term, in our lossy case, your sigma is larger than omega epsilon. This one is larger than this one. What happened? If this one is larger than this one, means the value of this imaginary part is larger than 1. So you cannot see the 1. Okay? Understand? This term is very large and this term is very small, means the total number is very large compared to 1. And that 1 is cannot see the 1. Okay, like if there's 1 minus J 100, 1000, if there's a number 1 minus J, okay, I can say that it's very similar to J minus J. Okay? Something like that. Okay? Oh. He is tired, it's okay. Okay, so
this one become here. I know it's very time, your energy consuming. It's hard to focus, but you need to train yourself to concentrate, to understand, and you need to improve your brain, like exercise, right? Like exercise. It's very hard if you don't usually exercise, but you do that every week. You have training, and maybe you can think more. Okay. Okay. So this term disappear equals to this one, and this one equals to that one. Actually, there is a small quiz here. Do anyone know this one? I will give. If you can tell student how to calculate that, I will give you an extra point. Or maybe I will ask you in the midterm. What is this one? Anyone want to try? Extra. Bonus. Bobby, do you want to try? You learned this before? This is the math. Huh? You know J, right? J is the square root of minus 1, right? Okay, sure. You are very good every time you answer my question. Good engagement. Let's try. Okay. Okay, if you think J inside, J outside, this is J also, right? I is J. No. J is your I. It's the same thing. Equals to the square root of minus 1. Then we just use J here because I is current. So no? You want to try again? Anyone? Oh, you guys don't know what is J? J equals to I. Do you know where the J come from? Because it is a time harmonic. So exponential J omega t, if you do the partial differential to time, will equals to J omega exponential J omega t. This is J, and the J is, if that is real, and the imaginary part, you have some number, the theta here. This is, yep, this is cosine theta, and the sine theta. Do you remember that? And then this is omega t, theta equals to omega t. This is where J come from. J equals to the square root of minus 1. Okay? Time harmonica. Time harmonica. So this one can, the real part has only cosine part, and the imaginary part is sine. And then sometimes we consider only the real part. Right? We did that in the IF class, right? IF system class. And also here, if there is a time. Okay? And there's a J. Yeah, I think you will remember. So when we talk about J, that's identical, the same as I, the square root of here. So you don't know? Come on. When we talk about Maxwell equations, you should already know what it is.
I don't know the left.
Okay. How do you remember this one? You forgot. What is this? If you want to calculate this one, for this term is easy, right? But there is a minus J here, right? The result is there is two parts. This is why that is a good question. So can anyone answer? No? Okay, I will leave the question to you. You want to try? It's fine. So there's no loss if you didn't get the right answer, but you learned something. One. Okay. We prove it. We prove it. So you square or equals to minus j equal 1? No. Right? You take the same thing itself. Yeah. How? You take a square, power 2, and you have the same result to prove your equation is correct. So equals to what? It's a fun question actually. For fun. I can tell you the answer, but you can think about that. Already, do you want to try? You forgot? Okay, good. Try to tell other students. Is that a remember? Supposed to be cosine theta minus j sin theta, right? You want to exchange? Cosine. Yep. Yes. Then, is that equal? And how about what is theta? I know you are close. You are close. Very close. But tell me what is theta? Degree. You can give me the degree about theta equals to the value of theta. Use the degree. Maybe theta equals to pi. Yeah, just put pi here. And we forgot the square root, right? Then equals to minus j, right? No. The square root is square. I mean the square root. Very close. Yes. There's a pi. Yes. That's correct. Yes. That's correct for the first step, then they also equals to square root of minus j, right? Go back to the same one, but I want the simplification. Then that equals to, okay, let me give you a hint. Okay, this one, that's pretty nice. Equals to explanation of something to the square root. Okay, so what is that? Right? Use the Euler. What is the Euler? The equation of Euler. If this is theta, but you use pi, right? exponential j theta equals to cosine theta plus j sine theta, right? This is cosine, this is sine. Okay, refer to
J
it's a positive or negative. So will equals to, you put a 1/2 inside, and equals to minus j pi over 2. So pi over 2 is 45 degree. 45 degree, and then you go back to the cosine and the sine for the 45 degree. Oh, no, 45 degree. Do you know 45? This is 45 degree, right? So cosine pi over 2 and the sine, what is the value of cosine pi over 2 and the pi over 2? You just put that back to cosine and sine. Okay, everyone got it?
Yeah.
Yes, it's a fun question. Actually, it's not difficult, but it's a fun question. And if you know that, you will get this one equals to this one. Okay. Okay, we will leave. You can get a point, but you are close. It's a difficult one. You can get an extra. Yeah. You want to try the rest? Okay. Please. Okay. But there is a positive and negative values.
Yeah, so let's say that. Just 90 degree and 90 degree. And yeah, so this is 0, this is 1. Oh no, set up. Right? Yeah.
Here is a square root we focus. Okay. And there's more. It will be a cosine and sine part, and you put. Yeah, it's pi over 4, not pi over 2, right? Abi, pi over 4. And you should put the pi over 2. This one is pi over 2, right?
Yeah.
Yeah, this is pi over 2. But I think you have the idea for the beginning, and then you can raise your hand high and give it a point. But you should make sure the details, and this is the idea. You put the square root outside. When I do the calculation about that, maybe you will have some question about the positive and negative side about that, but it's close. So equals to 1. Then this is a minus 1, right? And there was another answer for the plus 1. This is 1 minus j, right? You still have an answer for the 1 plus answer. This is the answer from the textbook. Oh, there's a 2 here.
omega epsilon, epsilon cancel out. And the omega, so you will have omega mu. The answer is 1 plus j times the square root of 1 over 2. Yes. There's another positive side here, so. Yeah. Please, okay, you can get a point. Okay, thank you. You have the idea for you to take positive and negative side carefully. For this one, you can get a half of the equation from here. Do you know why? The answer is a little bit different. When you take the half for minus j, there are 2 minus j. Actually, we do a research about this one. Okay, for this is real and imaginary. This one is minus j, right? Okay, then if you think this is a theta, you will get this point. You take a half of this theta, okay? But if you take this is a theta, you take this point, you take half of that. So your answer will be different if you do this one or this one. Understand?
你说是4分之2还是对的？它为什么在外面？
正跟负为什么？哦，跟它是这样的，你是4分之派是这边吧？假设这边对不对 ？cos 45度啊。
这边的派是
派是180除以4嘛，是不是45度？45度是 cos 是2，是跟就是2，对啊，根号2根号2。Okay, so you may have a different answer according to you regard this theta from this point. Half this one. Pi. Okay. If you take this one, you take a half, you will have this point. There is another way to think about that. Maybe your theta is from here to here. Now you take the half of that, you will get this point. Okay, so you take this point, or you can take this point. For this one is, you will have something is 1 minus j and over square root of 2 if you take this point. And then if you take this point, will be minus 1 plus j over by 2. And either way is different.
is because of the J outside. Yeah. J. Yeah. If you take that and multiply by J, will equals to J plus 1 over 2. Oh, yeah, this is right. You guys get it? There's a J outside, right? So you use your J multiply 1 minus J over square root of 2. And you get J 1 plus J over 2. This is just fun, and your textbook have the result. You can refer to the result in your textbook. This is my question. And what is the square root of J minus J? What is that? And, okay, I find it out. Okay, that's why you have 2 terms. You have 2 terms, and you have 1 over square root of 2 according to Euler. Okay, and both of you can get extra marks. Okay, and also there is skin depth. Skin depth, similar, right? Alpha is the same. The alpha, and also mention the skin depth. Okay, so finally we will have a table 1.1. So you guys still 1.1, or we have different version of the textbook. Check your textbook, the same one. Is that table 1.1? Right? Did you see the table 1.1? The same? No? 1.2. So for you guys, it's a table 1.2. Right? You got a result. There are 3 cases, like what I write down. Okay? For the textbook, you have maybe more accurate result about 3 conditions. If that is a lossless, your absolute double prime and your conductivity, both of them are 0, and all of the result, the gamma, original one equals to alpha plus J beta, right? But for this term, for your lossless term, it equals to only Jk, or you say J beta. So it is J times omega square root of mu epsilon. Okay? And your beta, it is K, it is omega multiply mu epsilon. Alpha equals to 0, and your eta impedance is what we used in your quiz number 3 to find out your edge, right? This is where it is. Well, in your skin depth, because it is lossless, your alpha is 0. 1 over 0, it is infinite. Your skin depth is infinite. And your lambda equals to 2 pi over beta. And the VP is omega over beta. Okay, you should be very familiar with this column, and use this table in your test. Maybe you can find an answer from the equations. Okay, this is an easy one for the lossless case. But if I ask you, if alpha equals to some number, or I give you conductivity, then you will use the general case. It's a lossy case. Lossy case. Okay? So your alpha will still become J omega multiply mu epsilon, but your epsilon, it is not a pure number. It's not a pure real number. It is a complex number for your epsilon. Then you can put them outside, looks like that one. Your beta, it is only your imaginary part. of your gamma. Okay, beta. Actually, I think there is a minus, right? Did he forget a minus? It's supposed to be a minus, right? J. Maybe omit the minus. Okay. Alpha equals to a real part of the alpha equals to the real part of gamma, and eta will become a new equation. Depends on your propagation constant. It is a complex number. This is a skin depth 1 over alpha, lambda the same, VP the same. Because it depends on your beta, right? Your lambda and the VP depends on your beta. You can see that even you have an attenuation, your propagation constant, your beta is the same, so your beta will not change according to alpha. So these two will be the same. Your speed and your length is the same, but you have an attenuation. Those are different. And for a good conductor, you have these conditions. When your epsilon double prime is larger, much larger than your epsilon prime, and your sigma is very larger than omega epsilon prime, so they are similar. They are similar. When you have that, this is what we calculate. You have this result, right? This is what we did for last page. This is what we did. Okay. You remember that one, but you forget this one is ridiculous. Okay, you should remember what we are doing here. We try to calculate what is the propagation constant if this is a good conductor. This one can become this one. Okay, and this is alpha, right? Alpha, it is, see that? This is alpha. And the alpha is skin depth. This is how we calculate skin depth. The same. So maybe I can ask you to derive the equation of skin depth for good conductors. This is how we derive it. Okay. So you got those numbers, you get this true the result according to this condition. And for other things, for these two parts, they are the same. And because your alpha, you already know your alpha, then you will calculate your skin depth directly, and you will get your eta impedance. They are a little bit different, right? This one and this one is a little bit different. Okay, this is a very useful table for 3 different materials, 3 different types of materials. Use the equations for the numbers in, get an approximate number to calculate. Yeah. Good for your midterm, this table, right? You can do you can solve a lot of problem by read this one carefully if you know how to use it. Of course you can find out, but you should carefully, you should know the condition. You should know why we can do that, and how to use the table. Okay, so this is what we obtained. Finally, we got a general case. It's a low C wave equations. They are low C wave equations. A little bit different, but maybe not so hard to understand, right? Now it's alpha, not J beta, it's just alpha.
and alpha equals to j alpha. Sorry, I always want to say gamma. Gamma equals to alpha plus j beta. Okay. Oh, so when I say there should be a minus sign, no, it's correct. Alpha, when alpha equals to 0, when alpha equals to 0, and beta equals to k, and here this is only the imaginary part here, right? Alpha is the real part and beta is the imaginary part. There's no question. Okay. Yeah, it's one of the result. And let me see what's okay. So this is the scalar, only the scalar term, right? In your test, I always ask you what is the final, the exactly term. You should put your vector, the unit vector outside. This is only for this one. I use another color. This one is purple one. The purple one is only the scalar one. This is only this part. Okay. You should write down vector outside for the total, because your E field is a vector. Okay. This is number only. Tell you about a magnitude, about what does it look like. You have an attenuation inside, you have a phase inside. Okay, positive way, negative, forwarding traveling, or forward traveling wave, and reverse traveling wave. Okay, let me see that. If I need to continue. Okay, we can take a little break. I will stop here, and then we will have one more hour to tell you something more. Okay. Okay, then after all, we can go back to very beginning. It is a general plane wave solution. Why I said the at very beginning? Because when we think about this question, I assume my electric field has only x component and traveling in the z direction, right? Remember, right? Your vector has only the component of x, but your E field is moving in the direction of z. It is a simplified, because I need to give you a direction if there is a plane wave. I want to explain this one, I want to ask you a question, I want to give you a quiz or midterm exam. You need to give me the number. You need a simple direction to show me you understand, okay? But in the real world, it's not true. You don't know where your E field go, right? You don't know where that go. So, what is the general E field? Your EM wave is traveling in the n direction, some direction. It is still a plane wave. It's traveling in not x, not y, not z. I tell you that it's in n direction. Okay? N is a combination of some x, some y, some z, but not total x, not total y, not total z. Maybe it has it's a x, y, z, right? But maybe there have a degree to each x, y, z, to each unit vector. Okay? You guys can understand?
this is a general case. Not only one single direction, it's a direction with maybe some x, a little bit x, more y, or a little bit z. Okay? Okay. To understand the physical meaning is easy. The difficult part is how to use your math to describe what I say. What is the general plane wave solution, more general direction of your E field? What is that? You will use a more general K and a more general vector R. Okay? Okay, let's start from the easy case. This is what we discussed so far for this one. So far, we use only, I have only S component. I'm moving in Z direction. This is the old story we have discussed so far. But in general, you should define this is like your X, only position. I think it's like this one, we define two new vectors. K become a new vector, and R become another new vector. Your K equals to is a combination of three direction, X, Y, Z direction of K. Okay? And you can combine them together and give it another new unit vector. I don't know where can n go. We don't know where is the direction of n. N is a general direction. Okay? Now it's not only S, and not only just X, Y, Z. It's maybe we try to consider all the possibilities. Okay? So our K will become your K to X direction, your K to Y direction, and your K to Z direction. Okay? Yeah, it's true. It's complex. It's a real world. Where we live is a real world. This is how we try to, we explain that in a very simple case. And I give you more, I give you more, I give you more. That's why I insist you should be very careful and clear by everything, details. Even you see the notations, you should know what happened. Okay? And for your direction R, it's not only, do you remember we have the exponential, maybe I just show you here. Here, this K, we are talking about something here, but you have extra X, Y, Z. Because you have three directions, so you need to write out. But here, you have only one direction. You don't need to care about it, right? Just only, for this one, just only Z. You don't need to worry about, you mix them up. But here, you need to consider a new general case. You need to consider how many K in X, how many K in Y, and how many K in Z. So you make a new notation which is a vector, not only just easy K. It is a vector. You have a X part, Y part, and a Z part. Okay. Same thing for Z here. When you think about Z here, there's only Z. You don't need to consider other things, just Z, right? But actually, if you have X, Y, Z, you need to consider not only x, but also y and z, and you need to put the vector here. What is your general case B is you need to use k vector dot r vector, and only if your right component multiplied by each other left. Understand? Xiong-sen is laughing. You don't understand, right?
Yeah,
You don't understand, okay.
that's so deep.
It's difficult. And let me explain something first to you. I simplify this one to only xy, okay? Maybe it's easier. Now it's xyz, right? xyz is more general. But how about xy? If I have a x direction and the y direction, okay? If there is a vector I call 1x multiplied plus 2y, okay? Okay? If there is a vector, something like that, so which means on the field, at every position, I might have 1 here and 2 here. So all the vectors goes to this direction everywhere. So like this one. Okay. If this is a vector, maybe say this is a vector r. Okay. I have only kx. K equals to ks multiply x. Means my wave there has only k in this part. If I do k dot r or equals to r dot k, I have only this part show up. Do you know the dot mean? I have only the component of x direction left. I don't have the direction go this way. How do I explain? It's like I think physically we have some examples. How to say that? Maybe I need to use that maybe in Chinese and English and deal with you. Okay, so I explain to you first. In physically, maybe we have something like you are doing you push object, but if how to say that? If your direction is not in the right direction, you don't have effort, the result. You don't make the power, or how do I say that? There is no energy in the same direction. If you push something in this direction, but maybe in here you don't count, you count only this part, so you check only this vector multiply this direction and you get a result. This is what we do, like do this one. For this case, because my k has only the part of the x, right? There is no y part. So actually, this term doesn't work. You got this term. Yeah, this is what we are doing here. But for the more complex case is for they separate something, a k for x component, and separate for y you have different k. For z you will have another k. So you just write down, and when you dot each other, your direction to x will become only this term. And to y and this term, and z this term. And for this n direction will be accumulation of s times kx plus y times ky times z plus kz. This is, you separate three direction, and we have three contribution to different direction. OK， 其他同学听得懂吗？这我要讲的是中文是 A。For the general case here, I think the only thing special is here. Your k has x, y, z, k, and it's a vector. Your r is not only z. It is now it's a vector of x, y, z. But is there any but? I think maybe yeah. The vector part is inside this E0, right? Still a vector. So something to come. Yeah. The only thing new is here. Focus on this part. Maybe you should focus on this part. Okay, and compare to don't have that. Compare it to this part. Okay, this is an easy case. Have only travel to z direction, and the result is going to x. But for here, you consider x, y, z is the result of x and y and z. You have different k for x, y, z. You have different position. Z is position. Z is the position. Z equals 0 means at the beginning, z equals 1, and you change the position. Z is where it is. Okay? Now R is not only Z but also X, Y, Z. Okay? General. So we can start to say more. Can we? Please? So now we open our eyes from simple E-field to a more general form. So we can think about polarization. 极化, polarization. Is you familiar with that? Polarization. Okay. What is polarization? Okay. Well, let me read. The plane wave discussed previously called linear polarization wave. Okay. So we learned so far it is a linearly polarized wave. Okay, just remember, it is linear, it's a line. It's an easy one, linear. The polarization of the plane wave refers to the orientation of the electric field vector. Orientation. How to explain this word? Abi, help.
Like direction?
Direction? Okay, where it is, right? Orientation, the direction of your vector. So, the polarization of your plane wave means where you put your vector, your E-field, orientation. Okay, which may be in fixed direction or may change with time. It's a big problem. Yeah, so far, maybe you will like fixed direction because it's easier. But now, there is something may change with time. Your direction of E field will change with time. Remember, I tell you that for this equation, for this point, what is the direction of E field in this case? X, right? But I'm telling you that there is some case, your E field is changing with time. Not only X, your E field changing, but you're moving, your direction of your wave is moving to Z, it's okay? But your E field, not only X, it will change with time. Can you imagine? Okay, let's see, did you, you use wave? Okay. Yeah. Okay, let's show, let me show you the result before we start to talk. I like this picture. If you take this before, maybe you have, maybe you remember something. Okay, this is what they are talking about. I like this one.
My name is Ella. I'm used to just learning math exam and watch a lot of YouTube. Brilliant is.
Okay, this is an easy case. I have not only the vector of x, y, and z, and move to the x direction. There is a, for this video, you have two vectors, E, Y, and EZ. And the green one is a summation of Y plus Z, okay? So your green one will look like that one, okay? But if these two E field have the phase change, you can see the green one. If these two vectors, the phase different, your direction of your E field will change with time. Do you want to see again? Okay. This is what the polarization means. Fun, huh? Beautiful and fun. I like this video. Okay. Again. Do you know the difference between this one and what we learned so far? Okay. So, okay. Let's stop here. I have two E fields. EZ and EY, but for our case, I always tell you EX, right? I just change a little bit. Your wave is moving in X direction, but your E field has only Y direction. Your E field is moving in X direction, but your field in the Y direction, okay? This is blue one only. We have learned so far is only half of it, just blue one. You just have another E field which is still moving in Z and X direction, but your E field has component of only Z direction. These two directions, these two E field, both of them are moving in X direction, but they have only Y component and Z component. Okay? When you put this E field together, you will become green result, green E field. That is E field of not only Y not only in z, is y plus z. And the result is also moving in x direction. Raise your hand if you don't understand, I will say it, okay? Okay? Understand? Not your hand if you guys had, okay? But if you don't move, I cannot tell you understand or not. You don't raise your hand, you don't nod your head. Are you listening? I will ask everyone, understand? 懂不懂？不懂，懂不懂？不懂，我再讲一次。Allow me to use Chinese, okay? 我们到目前为止，我出给你们的题目，它就是只有蓝色的，它就只有蓝色的。但只是我的题目是，我们之前讲的是 EX， 但是它往 Z 方向动，对不对？
对。
题目是说 EX 然后往那一样嘛。我只是说 EY 然后往 X 方向动，只是它这个它 XY 跟我方向不一样，这样好吗？所以你看到的蓝色的线就是我们目前为止教的方向。So blue one is what we learned so far. Just I change X Z to Y X. The same thing, totally the same. I just change X Y Z. Okay, okay. The blue one 好蓝色。但是我们刚才有讲过，你实际上不会只有 X 而已，你实际上是 X Y Z 都有，对不对？那但是这个 case 我再加一个就好，我不要让你太复杂，我再多一个红色。那红色它也是一样往 X 动，但是它的方向是往 Z， 这样可以吗？我只是换标号，有同样的题目而已嘛。I'll be okay. I just change. For the red one, I just change. We was asked to move to Z direction. But for the red one, I change that to Z. I change Z is only a vector Z. Move to the Y direction. Okay. Let's do some quiz. Okay. So everyone, I see it. Okay, so do anyone have paper? Who don't have paper? I want you to have a. Let me know if you don't have any paper. I want you to write down answer. I want to see your answer to make sure everyone understand. You have paper? Do you have paper? Bring your paper, okay? You have paper right now? Yeah, write down, make sure you are totally understand. Sometimes you think you understand and what's your answer? Okay. I want you to write down exact equation of the green E field. Right now. Question is easy, right? My question is easy, but your answer will be complex, complicated. Right now, I will see who can answer my question. E, okay, I give you more hint. Equals to E Y plus E Z equals to, write down these two. For a maybe lossless case, you use K is fine. And only for positive term is fine. Only positive term. Okay, everyone write down and I will see who can get extra point. For you, Abunsho and Abi, you already got extra point today, but you can still write down. I want to make sure you follow. Write down move to positive. I want to move to the positive z direction. The positive z direction. X direction, sorry, X direction. Only positive part. I want to write down the vector, maybe unit vector, everything. Write down this. I want you to turn in your answer. I'll give you extra time if you can answer it. And just write down. Yes. You can use something like E. Maybe something. Maybe they are the same, right? For this term, for the magnitude, maybe you can use this notation. You have some, but like in that case, they are the same, right? Or you can use the same notation and multiply something and then vector. Exponential. And I almost done. I almost finished to write the answer for you. And maybe the unit, don't forget. I always like to ask unit, it's important. Don't forget a unit, write the 4 equation down to me. Only positive wave is okay. Only forwarding wave. You can use K, use beta, either way is fine. For the lossless case. Extra point. You have many opportunities to earn your point. Actually, give an extra point to RB and Huensho first. Oh, I didn't check. Everyone come. 蔡伟翔，文修，蔡月婷，于其俊，张祖恩，黄柏成 ，OK， 许荣思，陈继轩，李坤灿，曾子轩，陈嘉义。蔡新君、张伟能、李冠毅、钟挺俊、黄德奇、张泽嘉、张佑宇、洪浩 ，OK， 你张小恩都没再来哦，阿碧和伟丽，边川派、胡文修、阿碧。
But I think it's there.
Okay, you done?
Yeah, almost.
Give me the paper and write down your name. Give me extra time. Let's see how many of you can answer.
Potential form? Is potential form?
Oh, okay, exponential form. Let's say use exponential form. Okay. And you can put time or not. Okay, you can put time, omega t. Time. Okay. 张佑宇、洪浩。 Be careful. OK， 继续的。圈。Check. Everyone can follow. Is that hard? You cannot make decision, right? You don't know what to put, what notation to put. You don't know. Yeah, if you don't know, I will tell you. But it's if I tell you how to remember, right? If you think and check, or you remember. That's my way. 加油！你行吗？你是对面好。这边对不对 ？OK。跟你说要写单位的那些。我知道单位啊。你知道单位跟你没写单位是两件事情。我就是一直讲，啊，大家拢赶快。来，我要期中考记得就好。OK。Who else？Who else？ 对不对？没有，就是说，我跟你说的，你没有养成习惯而已。来，来，你是谁呢？OK， 有名字就对了。OK， 你给了吗？给了吗？那下面这么拿来。OK， so everyone clean, right? 你还没吗 ？Come on， 考了你那么多次了，你是不好意思的吧？可是这个已经一直那个，你发了不上，我很难接啊。好，大家加油！太久了啦，单位忘记了。So maybe some of you still will forget the unit in your midterm again. I guess, okay. Yeah, there are many forms, right? So maybe you are confusing about a lot of things. So what is the answer for me here? I will use. Okay. Maybe you just want to see the right answer. So I just told you that if the magnitude of these two fields they are the same, if okay, supposed to be E0 multiplied times exponential minus J K, I go to X direction, right? This is important. Now it is X. Okay. If you put the time or not, it's okay. Or this time is okay. This is a time function here. Okay. For this one, it is direction is to Y. So it is Y. And this is only this term. Plus E exponential minus J K x, also x, moving to x, right? Exponential j omega t and z unit is v over m. Okay? Any problem? Maybe you don't have this term, it's okay. It's not a function of t, but you put this term, it's also a function of t.
Can combine?
Huh?
Can combine?
Combine, yeah, of course. Of course you can combine, but you should separate the vector. You can check E and maybe for other parts are the same, right? Yeah. Because you can combine, so this one will equals to exponential, but E0 exponential j omega t minus kx, and your vector become direction z y plus e. Okay, so this is the green one. The green one. Why you have a cosine? Because for this part it is cosine omega t minus kz, kx, this one, or this one, can change that to only real part. Cosine omega t minus kx. So you see a cosine here, right? Exponential, the real part of the exponential, you have only. So the equation, one is a red one is a blue one. You put it together, so your vector will become the 45 degree to y and z. So the final, this is like one unit vector to y and z. Or maybe you will say that your magnitude is larger than E0 because you have the combination. It's the square root of 2 times 1 times your E0. Right. Yeah. And then now, for the polarization part, we will explain that next week. But you will see that if for this one and this one, if they have a phase difference, they will turn. This is polarization. The linear polarization and circular polarization. We will talk about that next week, okay? About a circular one. Alright? That's it for this week. OK 吗？是有相位差的。